Hey everybody, I hope you enjoy Hacktivity so far, and I'd like to thank you for joining me for this talk. I'm Tamas. I'm a pentester and developer for a small IT security company in Hungary called PR Audit. I was part of the team Proditors who won the Hacktivity CTF in 2010 and 11, I think, and also won the European Championship of the Global Cyber Olympics in 2012. I'm a regular speaker at this conference, and I've also gave a talk last year and this year at DEF CON. Okay, so the title of my talk is Help, I've Got Ants. What are we doing with ants? Last year, in my talk, I've targeted one of my hobbies, flight simulators and other games. It was fitting to do the same to my other hobby, it's mountain biking. By the way, when I was doing this slide, I just realized that all of my hobbies include crashing, mountain biking, IT security, and flight simulators. I don't know what that does about me. Okay, so mountain biking and ants, what? There's lots of gadgets, lots of equipment that are involved in this sport and other sports as well. Old school speedometers got replaced by fairly powerful computers that talk to various sensors, speed sensors, heart rate monitors, etc., talk to your mobile phones and your PCs. And one of the protocols these computers talk to each other is called AND. It's also used for other purposes, for example, for weight scales, blood pressure monitors. Also, there are a lot of mobile phones that include AND chips, and also there's a mesh chat application called FireChat that can use AND besides Wi-Fi and Bluetooth. Okay, so in this talk, I'm going to speak about the AND protocol, the AND Plus and AND-FS protocols that are built on top of AND. I'm going to show you some protocol level design errors, and I'm also going to show you some implementation errors in various Garmin devices. Okay, so what is AND? AND is a wireless network protocol. It was designed by Dynastream for low-power devices. It's a 2.4 gigahertz. It operates in the 2.4 gigahertz ISM band, just like Bluetooth or Wi-Fi. The participants in the network are called nodes. There are slave and master nodes, and these nodes communicate with each other via mutually established channels. Each channel has lots and lots of properties. I'm not going to talk about every one because they are not that important from a security perspective. One channel property I'm going to talk about, it's called network key. It's an 8-byte number, and it is considered a security measure by Dynastream because only master and slave nodes that have the same network key can talk to each other. So it sounds good. Both nodes have to know the network key, but there's some catch. These keys are managed by Dynastream, so there's if you try to use a network key that is not released by Dynastream, then the hardware will default to a known key. So you can't just key any key in your application. And also the majority of equipments that use AND actually use AND Plus or AND-FS, and they are both managed AND networks, and they have their own network key, and these network keys are well known. They are on the slide. So it can be a security measure, but in practice it is not. Okay, what other security measures are in AND? There's a pairing bit. It is used when establishing the channel between two nodes. Two nodes can only communicate with each other if they have the same pairing bit. So it does not have to be on, it just has to be the same. So it is fairly trivial to circumvent this protection, because if you start two channels, one with the pairing bit off and one with the pairing bit on, then one of them will succeed. I have first realized that there's something wrong with, with pairing when I get home from a bicycle trip and looked at my FreeTNXT's graphs, and I saw that there are some heart rate data, despite the fact that I don't have a heart rate monitor. So it must have picked up from some other sources or something like that. Okay, so I'm going to show you how easy it is to spoof and sensor data without pairing. I'm going to show you this with my Garmin FreeTNXT watch. I'm just setting up a power meter, an AND power meter. Okay. Okay, so the watch now accepts power meter data, but normally a power meter should be paired with watch. But I'm gonna use the Simulant software, which was released by Dynastream to test AND devices. And I'm going to create a fake power meter. I'm setting a power value and starting the simulation. And the watch should pick up the signal, and yeah, it picked it up. So without pairing, we can spoof and sensor data. It's that easy. Okay, other security measures in AND. There are so-called inclusion and exclusion lists, white and black lists. They are essentially the same, but one for the slave nodes and the other for the master nodes. They are basically white and black lists for device IDs. The only problem with this is that only recent AND chips include these features. So for example, my FreeTNXT and my VivoFit can't use these features. Okay, there's also, according to the documentations, there's also an encryption in AND. So you can encrypt the data on the channel, but there are some drawbacks here too. It can only be used without shared channels. So creating topologies where, for example, multiple sensors speak to one computer is not that easy. It also requires the so-called advanced burst data, which is highly energy inefficient, which is kind of a problem for low energy devices. And the biggest problem is that encryption can't be used if you use AND+. And I've said earlier that the majority of devices on the market that use AND actually use AND+. So you can't use encryption. Okay, what's this AND+ I'm talking about? It's another protocol. It's built on top of ANT, and it basically just specifies some so-called device profiles. These device profiles are, like the network keys, are managed by Dynastream, and they govern some characteristics of the ANT connection, like the frequency, the network key, channel period, etc., etc. Some examples: it's a bicycle rear view radar and light, which utilizes the radar and light device profile. Dropper seat post that uses the seat post device profile, bicycle light with the light profile, and blood pressure monitor with the blood pressure monitor device profile. So these are just some examples of ANT+ device profiles. One of the ANT+ device profiles is much more interesting than the others. It's called Sync. And it is used to collect and transfer sensor data from sensors to ANT devices, and from ANT devices to PCs and mobile phones. This sensor data is stored in a storage format called FIT, and the data transfer protocol is ANTFS. And I'm going to talk about ANTFS now. About FIT, a few words first. It's basically the file format for ANTFS. It's pretty simple. It has, every file has a 14 bytes header, and after this several records, and each record has a 1 byte header and an arbitrary length of data, and the whole file has a 2 byte CRC at the end of the file. Okay, the reason I'm talking about FIT because my first attempt to hack my FreetonXT was to create some FIT files with fuzzing that hopefully crash the device, or hopefully enables to run some code on the device. So I've started with the FIT SDK and gave some sample FIT files to American Fuzzy Lab, and I've got some crashes, but they did not seem to be exploitable. Despite this, I've tried to upload them to the FreetonXT because I was hoping for some crash dumps or some error logs, something like that, but got nothing. The watch did not crash, but the ANT protocol stack became unavailable for a few minutes. This got me thinking that maybe the watch uses the so-called integrated profile, integrated ANT profile, which means that the ANT chip itself handles FIT. I was not able to verify or deny this. It requires some more work, but it would be interesting to exploit not the MCU, but the ANT chip itself. Okay, so back to ANTFS. It is a highly reliable and highly secure file transfer protocol built on top of ANT. At least that's what Dynastream says about it. If you Google Garmin ANT or something like this, then you will find some very serious rants about the reliability of this protocol. But now I'm questioning the security part of the statement. There are two major security features in ANTFS, according to Dynastream. The first one is the built-in encryption. So your FIT files can be stored encrypted, but none of the devices I've seen so far uses this encryption. And the other security feature is the multiple authentication mechanisms. So you can choose from 3 of them. I will show you this now. the first authentication mechanism is not really authentication. It's called pass-through mode, and basically means that if a host asks nicely, the client grants access. So I'm not sure what was the purpose of this. Maybe it is just there for testing or something, but it's not really authentication. So the second one is pairing mode. This has nothing to do with the ANT pairing. It's an ANT-FS pairing. It requires user interaction. It's basically the same pairing that you are used to in Bluetooth devices. So the host sends a serial number and the name for the client displays this name or the serial number and asks the user if the connection should be made. If the user accepts, then a passkey is sent from the client to the host, and the host stores this passkey and uses it for any further communication. So the pairing has to be done only once. Okay. So what attacks are possible against pairing mode? Of course, as a malicious host, you can send whatever network ID, whatever device ID, and whatever friendly name you want. So you can maybe social engineer somebody to allow a connection. But there's another there's another attack method. The passkey is sent on a successful pairing, so it can be sniffed. How do we sniff ANT? The NRF24 AP1 and AP2 chips that are built into the VivoFit and the Freeton XT are based on the NRF24L01 Plus chips, and as I've said earlier, they use the 2.4 GHz ISM band. They have 1 megabits per secondum on our data rate. They use GFSK modulation. And according to one documentation, the actual packet format is enhanced shock burst. So I've tried to sniff ANT packets with an RTL SDR. I found a blog post detailing how to sniff NRF24L01 packets with an RTL SDR and an MMDS down converter. And I've tried that with ANT, and it almost worked. Almost, because every byte I've decoded, every value was double of what I've expected. First, I didn't know why this is. The documentations does something about encryption, and my first thought, jokingly, was that maybe they used multiplication with 2 as an encryption algorithm. I've seen some pretty dumb shit from developers, but this would have been a whole new level of dumb. So maybe a more possible reason of why the values are the double of the expected is that the documentation lied and the packet format is not really enhanced shock burst. I've poked around a bit, and it turned out that there's a plain shock burst protocol, and shock burst and enhanced shock burst differ only in a so-called packet control field, which is 9 bits long. So if you try to decode shock burst packets as enhanced shock burst packets, there's a 1 bit left shift, which is multiplication with 2. So it was pretty obvious that after this, the actual packet format is shock burst. So I've implemented First, I've tried with RTL FM, and I've wrote a shockburst.c and an anteater.py to do this decoding, but it was not really nice, so I've implemented some Potosphere blocks to do the same. This is the hardware I used. And if you don't know Potosphere, it's something like GNU Radio companion. Okay, so I'm using a virtual machine with two ANT chips, one for the host and one for the client. And the software I'm using is the NTFS PC client and the NTFS PC host. They are released by Dynastream for testing purposes. So you can see the Potosphere topology, and I've started the client beacons, which you can see on the screen. This is a link command which sets the further frequency. Some more beacons. Okay, we are trying to download the directory, so there's a directory request. This is the directory list. It's not yet parsed by the plugin. And yeah, this is where the transfer failed because my USB ports couldn't handle it. So, but this shows that sniffing and NTFS is pretty easy, even with an RTL SDR. Okay, so back to the authentication methods of NTFS. There's only one left, the so-called passkey mode. Passkeys are up to 255 bytes long, so brute forcing is not feasible. But there's an attack mode against pairing mode too. So I've said earlier that after a successful pairing, the host remembers the passkey. The host stores these passkeys in a dictionary format. So for this client serial, that passkey. For that client serial number, another passkey. And if the host finds a client with a known serial number, then it sends the passkey to the client. This whole process could be man-in-the-middle. So using the NTFS PC tools I've shown you in the video, we can pose as a host and also as a client, which I did, and I've expected to find every info, even the passkey in the debug logs, but it was not possible because of the actual passkey check algorithm in the host. So I've had to patch the tools. I've started to binary patch the library, which contains this code, the ant-wraplib.dll, but realized that Dynastream released the sources, so it was much easier to modify the C code and recompile the DLL. So after I did this, it was possible to do this man-in-the-middle attack. So as a first step, we pose as a host, an NTFS host, and get the client's serial number. Here I'm setting up an NTFS PC host that accepts connections from any clients. Okay, maybe. Okay, I've opened the channel and started searching, and this is my FreeTNXT. It's not very fast, but it should pick up the watch momentarily. Okay. Okay, so the NTFS PC host found the watch. And you can see the client information, the device ID. Next step is to use this device ID to impersonate the client. So now I'm going to use the NTFS PC client and create an NTFS client with the device ID I've just gathered by posing as a host. Okay, so there's the device ID. Opening the channel, opening the beacon, and I'm going to start Garmin Express, where I have the FreeTNXT registered. And Garmin Express tries to connect to NTFS PC clients because it thinks that it tries to connect to my watch. And now I should have the passkey in the debug logs. And yes, I have them. Yes, that is the pairing key Garmin Express sent me. And now I can use the NTFS PC host again, using that passkey to connect to my watch and download files from it, upload files to it, etc., etc. So setting the key, opening the channel and searching for the watch. Again, it's not that fast. Okay, it found it, and using passkey authentication, you can see that it succeeded, and I could download the directory listing from the watch. So this man-in-the-middle attack is feasible and works. Okay, so this was the part about the protocol itself, about the protocols themselves, and a brief summary. Basically, it's all crap. So there is a possibility that ANT can be used in a secure manner, but you can't use ANT+, you can't use ANTFS. You have to create an own protocol based on ANT. You have to purchase a private network key, and also you have to use fairly recent ANT chips that implement the black whitelisting and the encryption support. Okay, so this was about the protocols. Now I'm going to talk about some implementation errors in various Garmin devices. I've targeted Garmin devices simply because of mountain biking, I have those devices. So I don't have anything against Garmin. The first thing I've tried is the pass-through mode. I said earlier that I don't know why they implemented it. It should not be there in production stuff, but it is there. So I can use pass-through mode to access the directory system, the file system of my Garmin FreeTNXT and also my Vivo Fit, and I suspect that all other Garmin watches and GPSs can be accessed with this pass-through authentication mode, which is basically just asking to connect. I've created a small proof of concept tool called hackend.py based on OpenAnt, and I'm going to show you this pass-through mode with that tool. So we are not specifying any keys or pairing or whatever. We are just asking for connection, and you can see that it was possible to download the directory listing. So this means that Garmin devices can be accessed without any pairing key, passkey, or pairing just by asking. If that's not enough, there's another flow. I was looking into the over-the-air firmware updates. It's an NFS feature. Some devices does not even have USB or any other means of data transfer, so firmware updates have to be done via NFS. And this process is documented by Dynastream, but it turned out that Garmin does not use that method. They use some own methods for this. So I've started to reverse engineer the Garmin Express software to see how it's done. While doing this reverse engineering, two method names caught my eye, those two. The compute factory paired device passkey and the has factory paired device passkey. So I was thinking that maybe there are some bundles, so they bundle a watch and the heart rate monitor, and they use these factory keys for these bundles. But nevertheless, I've tried it with my Garmin gadgets, and it worked. So this is the algorithm. I've also implemented it in hackend.py. It only requires device ID, and from that it calculates a passkey, and that passkey can be used to access the file structure of these devices. So basically, this is it. When the client connects, it gives us the serial number, and from that serial number, we can calculate a passkey that can be used to access these devices. Okay, so serial number, as I've said, it can be read when the client connects, but it is also printed on the device or the packaging, so you can basically just walk into a store, write down the device ID, and hack the devices later. Okay, back to over-the-air firmware updates. With Garmin stuff, it works like this. The updates come as RGN files. These are so-called region-wrapped firmware files. They have to be unwrapped, and this unwrapped firmware has to be uploaded to the NFS directory structure at the first index as a device file type. So it's basically just an upload. I've tried modifying firmwares and uploading them to the devices, but it did not work. So it was obvious that there is some integrity checking. So I started looking around in the firmwares and found two CRC16 tables and also two CRC16 function implementations in the, I think it was the VivoFit binary. It turned out that CRC16 was not the algorithm used for checking the firmware, but finding these was still useful because the functions used direct addresses to the CRC16 tables, and this made it possible to deduce what address the firmware is loaded. So it's a nice example of how some failed paths can lead to useful information. It happens a lot in hacking, I think. Okay, so the actual CRC algorithm was much, much simpler. The sum of all bytes had to be 0. So the actual checksum is the last byte, and it is pretty easy to calculate. So I have created this fix crc.py, which fixes the CRC, and I'm going to show you how to upload a modified firmware to the Vivo Fit. So I'm just replacing a string. I'm doing it with radar because why not? Okay, instead of sleep, it should display hacked after uploading. Now we have to fix the CRC and upload the firmware to the device. It can be done with Hackant. And I'm using pass-through mode. This is the default in account.py. So the firmware update started. I'm gonna speed it up. Okay. So we can see that the firmware update succeeded, and when we try to put the Vivo Fit in sleep mode, it should display hacked, and it does. So it's that easy to upload the modified firmware to the Vivo Fit. Okay, one interesting thing, when I was poking around in the Vivo Fit firmware, I've spotted an XML string. I really love XML because there are some pretty fun bugs that XML is involved in. So I started to looking at this XML file, XML string. There was two suspicious values, a bunch of X's and another node with one X. It turned out that the bunch of X's is a placeholder for the device ID, and the one X is a placeholder for whether heart rate monitor is used or not. So it was pretty obvious that this XML is some kind of device descriptor file. But where is it used? NTFS deals with FIT files, so it can't be an NTFS feature, but the Vivo Fit is also Bluetooth Low Energy capable, and it uses it to connect to the Garmin Connect mobile application. I've started to reverse engineer the Garmin Connect application and found a function that downloads this XML string from the device. So I thought that if I could modify the XML string in the Vivo Fit firmware to include an XXC vector, then I could hack my phone. So I modified the firmware, uploaded it to my Vivo Fit, and tried to connect my Vivo Fit to my mobile phone while listening on my server for the connection from the XXC vector. And the connection came, but it did not come from the phone, from my network. It came from a Garmin server. So the phone downloaded the XML string from the Vivo Fit firmware and sent it without any modifications to a Garmin server, which was susceptible to XXC. And this way I could hack one of the Garmin servers. So it was a kind of funny way to find a vulnerability in one of Garmin's internet-facing servers. Okay, so basically this was the last thing I wanted to tell you. A brief summary. Ant is bad. Ant is not secure. It's pretty easy to sniff. It's pretty easy to to do man-in-the-middle against it. The security measures are not really security measures, they are easy to circumvent. Basically, anybody who can get a few meters close to you or your device can upload or modify a firmware on your device without your knowledge. Thank you for listening to me. If you have any questions, I don't know if I have time, but I will be in the speaker room, or I don't know what that's called. Thank you.